Hydrogen is the most abundant element on the planet and the cleanest source of energy. Hydrogen is already important in some parts of the energy value chain. Early hydrogen storage tanks used in fuel cell electric vehicles were highly pressured in liquid, cryo. Unfortunately, fueling these tanks is expensive, and the supporting infrastructure requires extensive maintenance. Furthermore, today's major sources of hydrogen gas are costly, energy-intensive processes. What if there was a new type of hydrogen that could be produced more cheaply, stored, and transported more economically without negatively impacting the environment? This is where solid-state hydrogen energy storage comes in. Because of its low volumetric energy density, hydrogen is difficult to store. It's the lightest and simplest element, weighing less than helium, and thus easily lost in the atmosphere. Another challenge is that liquid hydrogen has a very low boiling point of 252.8 degrees Celsius, which means it must be cryogenically stored at low temperatures. Storing hydrogen as a gas presents additional challenges because it typically necessitates the use of high-pressure tanks, 350 to 700 bar or 5,000 to 10,000 psi. Hydrogen can be stored using materials in addition to being compressed as gas or stored as a liquid. There are three types of hydrogen storage materials: those that use absorption to store hydrogen on the material surface, those that use absorption to store hydrogen within the material, and those that use a combination of solid and liquid materials. Absorption occurs when hydrogen molecules or atoms attach to the surface of a material. The hydrogen in this method binds to materials with high surface areas, such as microporous organometallic framework compounds, metal organic frameworks, MOFs, microporous crystalline aluminosilicates, zeolites, or microscopically small carbon nanotubes. Because of the increased surface area for the sorbent, hydrogen absorption to powdered materials can achieve high densities of volumetric storage. Hydrogen is dissociated into hydrogen atoms during absorption and incorporated into a material's internal solid lattice framework. The third of these hydrogen material storage systems, hydride storage, can use the reaction of hydrogen-containing materials with water or other liquid compounds, such as alcohol. This method of storing hydrogen, also known as chemical hydrogen storage, effectively stores the hydrogen in both the material and the liquid. The hydrogen in metal hydride storage systems forms an interstitial compound with elemental metals such as palladium, magnesium, and lanthanum, intermetallic compounds, light metals such as aluminum, or some alloys. These metal hydrides absorb molecular hydrogen onto their surfaces before incorporating it in elemental form into the metallic lattice through heat output. They can be released again with heat output, and these hydrides can absorb large volumes of gas, with palladium, for example, absorbing 900 times its own volume of hydrogen. In addition, hydrogen can be chemically bound with a liquid organic hydrogen carrier. These chemical compounds, which include the carbazole derivative N-ethylcarbazole and toluene, have a high capacity for hydrogen absorption. Large amounts of hydrogen can be stored by materials with smaller volumes, lower pressures, and temperatures close to room temperature using these material-based methods. Volumetric storage densities greater than those of liquid hydrogen are possible with material-based storage. However, materials-based storage is still in the works because the cost of charging, discharging, and processing hydrogen is still deemed to be prohibitively expensive and time-consuming. Plasma Kinetics, a small Arizona-based clean energy startup, has developed game-changing solid-state hydrogen technology that could forever change transportation and destroy internal combustion energy, ICE vehicles, obsolete. The technology is so disruptive and transformative that the U.S. government prohibited it due to the ITAR, International Trade in Arms Regulations, embargo, which means the startup could not export the technology for missile fuel, which the founder claims was never the focus of solid-state hydrogen fueling. Unlike the current liquid hydrogen used in today's fuel cell vehicles, which require significant amounts of energy and resources to produce, this new solid hydrogen technology is so revolutionary that the U.S. government banned it when the company first introduced it in 2008. According to Plasma Kinetics founder Paul Smith, the U.S. government initially called it transformational, then changed it to disruptive. Unfortunately, the U.S. government slowed the company's research by restricting its patents until 2017, when the restrictions were finally lifted, allowing Plasma Kinetics to commercialize the new technology and sell its products on the open market. Green hydrogen has been touted for many years as one of the essential ingredients for the future sustainable energy mix. But it has failed to deliver due to the invisible, yet the big problem of storage, transport, and operation. Plasma Kinetics is the first to address these issues. It is also the only hydrogen energy system that provides zero-carbon hydrogen capture, storage, and delivery. According to Plasma Kinetics, the majority of hydrogen used today is derived from natural gas separation and electrolysis, which consumes a lot of energy and necessitates energy-intensive compression or liquefaction to store. As a result, the transition to hydrogen as a viable alternative to lithium-ion batteries is hampered primarily by a lack of cost-effective infrastructure capable of efficiently capturing and transporting hydrogen gas. Plasma Kinetics technology can capture metric tons of hydrogen per day while emitting no carbon. Furthermore, the startup claims that it requires little infrastructure and can safely transport hydrogen around the world. Its technology is based on a layered nanophotonic structure that interacts with light via a proprietary shape memory alloy. Individual layers are only a few angstroms thick, and nanolithography creates surface structures that allow hydrogen to be released with light. Plasma Kinetics captures gas from smokestacks rather than the two most common methods for producing hydrogen: steam methane reforming and electrolysis, splitting water with electricity. The hydrogen is then extracted from the gas and solidified. Plasma Kinetics employs a carbon-free capture method that reduces greenhouse gas emissions while producing hydrogen via a process known as light-activated hydrogen. After shining a laser on a lithographed hydride in the form of a light-activated nanostructured thin film, hydrogen is released. Plasma Kinetics then uses a microwave to store the hydrogen. Green solar to hydrogen or wind to hydrogen electrolysis is also captured by Plasma Kinetics technology. Storage is 30% lighter, 7% smaller, and 17% cheaper per kilowatt hour than a lithium-ion battery. Plasma Kinetics said, "We are able to remove greenhouse gases from smokestacks, capturing metric tons of pure hydrogen from the steam without needing to use any energy. No pumps, no electricity, no chemicals, no energy. We are the only solution which can claim 100% carbon-free absorption, storage, and delivery of hydrogen. Our products are recyclable, and our manufacturing is 100% zero carbon. No other technology can make this claim." Plasma Kinetics announced that it will enter commercial markets with a follow-on technology derived from a U.S. Department of Defense application that captures hydrogen, stores it for long periods of time, and then releases it for stationary and transportation applications. At standard atmospheric pressure and temperature, Plasma Kinetics' proprietary nanophotonic material absorbs hydrogen, according to the company. The material absorbs metric tons of hydrogen in minutes. Hydrogen is released by controlled light at 99.99+% purity, Plasma Kinetics said on its website. If the technology lives up to the hype, it has the potential to disrupt the current EV market, and Tesla may be the biggest beneficiary of this solid-state hydrogen technology, despite Musk's previous dismissal of the legacy version of this technology as fuel cells. While Tesla CEO Elon Musk is currently the world's richest person, worth around $300 billion, the technology has the potential to make Musk the first trillionaire in history. What are your thoughts on it? Let us know in the comments below.